Chapter 1-4, Continuity. In calculus, you always want to work with a continuous function. Now that doesn't always happen, but a continuous smooth function has less problems than one that has sharp turns or a break in the graph. So today we're going to talk about continuous functions. And whether or not a function is continuous or not is intuitive. You can look at the graph. And let me pull this graph up. And I don't think any of you will have any trouble saying that this function is not continuous at 1 and at 2. And we're talking about the function, let me go back, pick up my pen. We're talking about the function y equals f of x over the domain 0 to 4. So the function's not continuous at 1 and 2. Now, in a second, we'll talk about being continuous at the endpoints. And since f of 0 exists and f of 4 exists, this function is also continuous at the endpoints. All right, there's 4 types of discontinuities. The first one is removable. And it's removable because if you had a function that gave you this graph, my pen again, that gave you this graph, you could rewrite the function such that the y value here, wherever the hole was for x, is filled in. So you could make it continuous by rewriting a new function. And right here, you could eliminate that y value, rewrite it, and fill it in here. So this type of function where there's a hole is called removable. These are not removable. The next 3 are not removable. You need to know all of these for the test. If you have a jump or a step, it's not removable. If you have an infinite going on, even if they're both going to positive infinity or both going to negative infinity, it's not removable, but it is also a type of discontinuity. And if you have oscillating, we looked at this in the calculator before, where as you're going to 0, the limit from the left does not equal the limit from the right. It jumps back and forth. So these are 4 types of discontinuities. Removing a discontinuity. Here we have a function x cubed minus 1 over x squared minus 1. And if you look at the graph of that in your calculator, you will see that there's a hole at x equals 1. You can further verify that by taking the limit as x goes to 1, and if you plug it in, you have 0 over 0, which is indeterminate. But if we factor the numerator, factor the denominator, we can cancel out at x equals 1 where the hole is. Now we plug in 1 and we get 3 halves. So at x equals 1, the hole is at y equals 3 halves. Remember, that's the y value. So if you wanted to remove it, you could rewrite a function where you rewrite your original function. Now this is how it's done. Rewrite the original function, eliminate where there's a hole, and then write the y value that you got here at x equals 1. Now note that there is also a discontinuity at x equals negative 1, but it can't be removed. And I have a graph of that coming up right there. So here we have an asymptote at x equals negative 1. And at x equals 1, we filled in that y value with 3 halves. 3 halves right there. At x equals 1, you have the point 1, 3 halves. So we remove the discontinuity there. We cannot remove the discontinuity at x equals negative 1. Now, the good thing about continuous functions, if you add them together, you subtract them, you multiply them, divide them, you still have a continuous function. Or if you take a continuous function, you multiply it by any real number, you still have a continuous function. And also, composites of continuous function are also continuous. And here's 2 examples. We know that the sine is a continuous function. We know x squared is a continuous function. So then this function, the sine of x squared, is continuous. Continuous. We know that the cosine of x is continuous. We know that the absolute value function is continuous. So this composite function is continuous. Now here's the continuity test. You must know this test in order and exactly as it's written. And it's over the set of real numbers. So if you have any function, y equals f of x, it's continuous at a next value, say x equals c, if and only if all three are true. Number one, f of c exists. The y value is there for that particular x. That makes sense. This is existence. The limit as x goes to c of f of x exists. And that just means that when you look at the limit from the left and the limit from the right, that the y value is the same. So the limit has to exist. And if it's an endpoint, you use either the left or the right hand limit for that. And then the last one, important, they have to be equal to each other. The y values have to be the same. The y values at c has to equal the limit at c. And that's the continuity test. Know everything in blue. And I think the last, on your PowerPoint, the last paper we'll practice it in a second. But before we do that, let's look at a theorem that we've seen before. If a function is continuous between a and b, then it takes on every value between f of a and f of b. So here's a function, and it's continuous on a, b, so that you know that it must take on every y value between f of a and f of b. And if you found some y value between f of a and f of b, you're guaranteed that that corresponding x value is between a and b. Now how can you use this to show existence? Here's an example. Is any real number exactly one less than its cubed? So say my real number were x. So I'm saying, does x equal x cubed minus 1? So my real number x is exactly one less than the cube of my real number x. Now note, it doesn't ask me what that number is, only if it exists. Okay, so if I bring over the x, I have the equation 0 equals x cubed minus x minus 1. So in essence, I'm saying, are there any x-intercepts? Well, we know by end behavior that there is one, but we're going to use the intermediate value theorem to prove it. So let's write this as a function. And if you look at this on the calculator, it's probably easier to come up with these x values. But let me get the calculator out and take a look at it. You might do the same thing. All right. So looking at it on the calculator, it looks like this. I did a zoom 4. Here's 1 and here's 2. Here's 1 and here's 2. So that when I looked at 1, f of 1 is equal to negative 1, and f of 2 is equal to 5. So I'm continuous on the interval 1 and 2, and my function must take on every y value between f of 1 and f of 2, and 0 lies between lies between negative 1 and 5. So therefore I know that my solution is between 1 and 2. If you use your calculator, you can find it approximately. It happens to be an irrational number, and there it is to 5 decimal places. So by the intermediate value theorem, I know it exists because this is a polynomial function. It's continuous on 1, 2. And so it takes on every y value between f of 1 and f of 2, or every y value between -1 and 5. 0 lies between -1 and 5. So therefore, there's an x value that makes this equation true, which makes this equation true, which makes this true. Okay? It's existence. We had to use our calculator to find out what the approximate value was. Okay, I'm going to pause this now and pull up the last sheet on your PowerPoint. Okay, we're going to use the continuity test to discuss the discontinuities of this graph, y equals f of x. Now, looking at this, you can say that it's not continuous at, let me pick up my pen, at x equals 1, at x equals 2, and x equals 5. And we're talking of the domain of 0 to 6 inclusive. So those are the 3 points that we're going to discuss the discontinuities. So let's start, and we're going to use the continuity test. And remember that the continuity test says, number 1, existence. Number 2, we're going to look at the limit. And then number 3, does number 1 equal number 2? And that's the question. All right, so at x equals 1. All right, does f of 1 exist? Yes, so you don't write anything down. Does the limit exist? No. As soon as you say no, then you know it's not continuous. So you're going to write down the limit as x goes to 1 of f of x does not exist. Therefore, discontinuous. All right, let's look at the second point. At x equals 2. Does it exist? Does f of 2 exist? Yes, it does. F of 2 is equal to 2. Does the limit exist? Yes. The limit as x goes to 2 is 1. Does f of 2 equal the limit? No. The limit as x goes to 2 of f of x does not equal f of 2. So therefore, discontinuous. So you only have to write down what's causing it to not be continuous. Number 3, at x equals 5. Does f of 5 exist? No. If f of 5 doesn't exist, it's not continuous. So f of 5 does not exist, therefore discontinuous. Now, if you did any other point, you would say yes, yes, yes. In other words, let's check out x equals 3. Does f of 3 exist? Yes, it's 2. F of 3 equals 2. Does the limit exist? Yes, the limit as x goes to 3 of f of x equals 2. Does f of 3 equal the limit? Yes. So all 3 you say yes, so it's continuous. If you say no at any of the 3, then it's not continuous. I hope this makes sense. Good day.